ladies and gentlemen. So we have a number of cool demos here today. We'll be cooking with induction ovens, among other things. So given that, this device does produce a bit of low frequency leakage currents if you're in large magnetic fields. In particular, this is a large electromagnet. If any of you in the front row have pacemakers, should probably step back, hopefully not. Or if you have credit cards, put them a little further away. So with that warning, first of all, let me see if you have any questions about the. Well, on this distance it should be safe, Or if it makes you feel any better, my credit card is closer. Yeah, I mean, if you come closer, after the class, make sure that this thing is off. It's a large electromagnet. Yes, it can demagnetize credit cards. That has happened to me. Well, not with this magnet, but that has happened to me with large electromagnets in the past. This one, by the time the field gets to you, it will be small enough. So let's see. So first of all, do you guys have any questions about the material so far? If not, again, a quick reminder, actually two things. One is that if you haven't seen your midterm reports returned to you, your midterm grades, they have been posted. I showed the distribution of grades last time. The GSIs in your next section will distribute the solutions, will distribute your Scantron pages and your short answer essays, and so you can look at your solutions and the grades. We have also posted the grading rubric, so you can actually look at it ahead of time if you have any questions or concerns, or if you'd like to request a regrade, which usually in this class is rare. So that's announcement number one. Announcement number two is, if you've noticed last week, we have posted a feedback form, kind of a little mini, it's not a quiz, I guess it's a survey. That's your opportunity to tell us what you think anonymously. You'll get 5 points on towards your homework for completing this form. It has, I forget, 8 or 9 questions. So this is your opportunity to provide feedback to me, to your GSI about what you like about the course, what you don't like about the course, and what you would like to see later in the semester. So the nominal deadline for filling it out was last Friday, but the feedback form is actually open forever. If you haven't filled it out yet, please do. And again, you get 5 points on the homework for doing that. So those are 2 quick announcements. In the meantime, we talked about electricity and electrostatics last time, and we'll talk about magnetism, which is another side of essentially the same effect. In fact, in more advanced physics classes, we describe magnetism as just a special case, another manifestation of electric interactions, electrostatic interactions, but interactions that happen because of motion of charges rather than from the static charges themselves. So it's another manifestation of the same phenomenon. We now describe electricity and magnetism as the same force, as something that is inherent to any particle that has an electric charge, like an electron and a proton, or a combination of those particles. And the only distinction is that if the electron is sitting at rest, sitting in place somewhere, it produces electric fields. if you make it move, it will produce electric and magnetic fields together. Or if you move relative to it. And so later in the semester, we'll talk about ideas of relativity, postulated and described by first Galileo and then Albert Einstein. And the fact that there's really no specific special point of view. There's no special reference frame where you can say some objects are exactly at rest and some objects are moving. In some sense, the concept of motion is relative. And so in that sense, our perception of electric and magnetic field depends on whether we look at a static charge or magnetic charge, and that part itself is actually relative. In some sense, electric fields can manifest themselves as magnetic, and vice versa, depending on whether you're moving relative to a electric charge or whether you're looking at it statically. So at least that's a conceptual description of electromagnetism on the fundamentally microscopic scales. On our human scales, we actually perceive electricity and magnetism quite differently. Ancient Greeks, and perhaps even before, have noticed that there are some materials that exhibit permanent magnetism. And clearly, so here's the compass needle that's supposed to point north to south. It probably got demagnetized. It sort of points in an arbitrary direction. Let's see. West is kind of that way, right? So this is sort of south, kind of. It sort of points roughly in the right direction. So it's been noticed that there are these materials, in particular iron, exhibits this property that it can attract to other pieces of iron or can repel from other pieces of iron, or needles made of these ferromagnetic materials would and placed on a pivot with low friction can orient themselves along the north-south direction in the Earth. And so this is now understood as a magnetic effect, or a magnetic field rotates the compass needle towards the orientation of the Earth's magnetic field, which roughly coincides with the, but not exactly coincides with the direction from geographic south to geographic north. So fundamentally, we understand this, that magnetic field comes from the spinning or motion of electric charges, but we observe this phenomena in a kind of more macroscopic sense. We look at magnets that are these things that have allegedly two poles, north and a south. North pole always rotates and orients itself along the direction of magnetic field towards the magnetic north pole that's somewhere in Canada. And therefore, the south pole would rotate in the opposite direction. If you take two magnets, I guess I should have brought some, and orient them next to each other, kind of like so, the north pole will be attracted to the south pole. And if you bring the two south poles together, or the two north poles together, they will repel. So this behaves somewhat similar to electric charges. Remember, we discussed electric charges that have positive signs and negative signs. Positives are the ones that produce by rubbing a piece of plastic against polystyrene, which ancient Greeks didn't have. Let's say positive produced by rubbing against your hair or cat or fur or some other fur animals. So there are two types of charges, and we can separate the charges by applying mechanical work and then have a positive in one hand and negative in the other hand. And magnetic charges or magnetic fields are somewhat similar. There is effectively a positive sign and a negative sign, except we talk about them as poles from which the magnetic field lines emanate, and historically, instead of positive and negative, we call them north and south because of how they orient themselves in the Earth's magnetic field. Clearly, this is useful for geography. This is useful for navigation, and ancient Greeks have taken advantage of that. You can build devices that will point along the magnetic field lines. And the behavior in terms of attraction of the opposites and repulsion of the similar poles is very similar to electric charges. And that's actually not a surprise because, again, fundamentally, the phenomena of electricity and magnetism are very similar as well. Just the motion of electric charges produces the field, and then depending on the direction with which the charge moves, the magnetic field will either point sort of one way or the other way. You make the electron spin one way, it will produce magnetic field that will point itself, let's say, outwards. If you make it spin the other way, the magnetic field direction will flip. So you can produce north and south poles by motion. Of course, in the materials, this is not obvious. So, I mean, it's a little more obvious with this example. The fact that you can produce motion of charges by sending electric currents through wires. And here's an example. I have two electric wires. I can send large currents through them. And okay, the video is on. And observe the position of the wires change slightly. If the camera can zoom in, and if you can look at it very closely, you would notice that the electric current, when I flip the switch and send the electric current to the wires, the position of the wires shifts slightly. In this case, the wires come a little closer together because I send the current in the opposite directions. It produces magnetic fields that attract each other. If I flip the direction of the current to send the currents in the same direction, now the magnetic fields produced by each of the wires will point in the same direction and then will repel each other. Let's see if this device is sensitive enough. And you can sort of, if the camera zooms in, you can sort of see that the wires spread out. Even more importantly, you can actually see these currents give an effect, produce an effect, hopefully, on the magnetic needle, on the compass needle. Now, so I orient this compass needle along the north-south direction. If I start the current, the magnetic needle flips. Oops. Oh. I was told not to do it too long, and in fact I melted the wire. This demonstration has a built-in fuse, which I now have successfully disconnected. The currents we're sending here are about an amp, and it's enough to melt the fuse, and I'll have to apologize to James, who will now have to resolder this connector. But hopefully before the fuse melted, you would notice that the magnetic needle turned. The magnetic needle turns towards this arrangement of currents. It points along the new direction of magnetic field that's now produced by these wires. So sending the currents to the wire produces a magnetic field that has an effect on the magnetic compass needle. So this fact has been recognized. It's recognized primarily. The studies of electric currents were done in the 18th, 19th century. Michael Faraday, who's now recognized as was a brilliant engineer, didn't actually have formal education, but did a lot of experimentation on currents and magnetic fields, have developed a set of rules which are now recognized, a set of magnetic laws that were then understood and combined by James Maxwell into the so-called Maxwell's equations that now describe the behavior of electric and magnetic fields. But these rules that Faraday put together primarily experimentally describe how electrical currents produce magnetic fields and how magnetic fields can produce electrical currents, sort of the mutual interaction between fields and currents. And this is now quite important. These effects now are used technologically to either produce motion from the application of variable magnetic fields, or the other way around, produce electric fields, effectively electricity, from the motion of currents in the magnetic field. The fundamental principle, however, is the fact that currents can produce magnetic fields. So you may ask then, well, here's, I guess, is another example. If the current sent through a piece of wire can reorient a magnetic compass needle. That by itself is the type of motion. But that motion, of course, can be much more macroscopic. I have here a very large solenoid magnet. A solenoid is basically a bobbin. If you guys know what a bobbin is, that seems to be a British word. A spool with a large number of coils, wire turns wrapped around it in a continuous way, in such a way that the wire stands on this end, and then I wrap around a whole bunch of wires, sort of like the thread spool that's used in sewing machines. It's wrapped around this spool, and the other end of the wire comes up on the other end of the spool. I can now connect this to a source of high electric current, send the current through. This current will generate magnetic field that in the solenoid points along the axis of the spool. So in this case, it will point in this direction. So if I turn the current on, now there's a field pointing in this direction. If I bring a compass needle, I guess it already points north-south, so that's not a good demonstration, but let me see if at least the direction flips. Well, I was told that this demonstration requires power. Okay, how about the following? Change the current, and clearly, start the current, and clearly something changes around this solenoid. We're producing now large magnetic fields that are pointing along the axis. So what do you think will happen if I stick a large piece of iron inside the magnet? Iron, as we have also learned historically, is an example of a magnetic material. It's so-called ferromagnetic. It sits here in the periodic table, kind of in the middle. There's several elements here that all have this specific property: chromium, manganese, iron, cobalt, nickel. In particular, these three, iron, cobalt, and nickel, that are called ferromagnetics. What it means is actually that if I apply a magnetic field to a sample of iron, the electrons in the iron will all want to reorient themselves. They're all sitting there in the atom spinning in random directions. Each electron has its preferred direction, but a large number of those electrons are completely uncorrelated to each other. They don't talk to each other much, so they're all spinning in various random directions. But if I apply a magnetic field to define a particular direction, all of these little spinning electrons will reorient themselves similar to this magnetic compass needle. They will reorient themselves along the new north-south direction, which, if I stick this iron core inside the solenoid, will be pointing along the axis of the solenoid. So ferromagnetics are examples of materials that can be polarized. They can be reoriented by a large external magnetic field. And so now, once I do that, once I reorient all of the magnetic directions for each electrons in the iron core, now this piece of iron will become a magnet itself. And that magnet can interact with the magnetic field of the solenoid, in particular be either attracted or repelled, either attracted or repelled from the magnetic field. Here's an example of this. Turn the magnetic field on, turn the current on, produces the magnetic field in the iron core, in the solenoid. That solenoid magnetizes the iron core. That magnetization produces large enough force to pull this block of iron that weighs a few kilos, 5 pounds or so, right inside the magnet. This is how your electric locks in your car work, well, on a smaller scale. You have the little clicker thingy, the fob or a button that you push that sends, if you have a fob on your keychain, it sends radio signals to your car. The car turns on a little circuit that sends a current through a small solenoid in your door lock, and that interacts with a hinge that's slightly magnetized, and boom, the door locks, or unlocks, as it were. The force produced by this magnetic interaction can be very significant. If I turn the field on and try to pull this magnet out, it's not going to budge. The forces, the attractive forces, can be very large because they're produced by a very large magnetic field produced by a large number of coils in the solenoid, and a large magnetization, large field induced in the iron core. If I turn the field off, the effect goes away. I can easily pull out my block. So again, if you want to unlock the magnetic door, you turn the current off and you can disengage. Which I guess is why in the various movies about heists, perpetrators always try to turn power off to, banks and vaults and other things they're trying to get into. Disengage magnetic circuitry. Now, at the same time, we know that there are also permanent magnets. So this compass needle has no current in it, right? No external sources of electric currents. So how does that compass needle work? Why does it produce magnetic fields? And it works, again, for this, there's this set of materials, and in fact, these guys, iron, cobalt, and nickel, some of them, they are these rare earth elements that you have heard about. For example, neodymium, which is here in the bottom somewhere, is another important element that have internal motion of the electrons, internal little compass needles that each electron possesses, oriented in one particular direction. So in these permanent magnets, the magnetic field is still produced by motion, by small electric currents, except that those electric currents are not provided by some external battery, but are internal to the atoms themselves. Each atom has electrons on the outer orbit. Neodymium, so iron has 4 valence electrons on the outer orbit. Neodymium has, I think, 5, if I remember correctly, 4 or 5. Each of them has internal sense of magnetic field. Each of them has an internal magnetic moment, internal little compass needle called a spin or a magnetic moment. And in some of these materials, just by the structure of the material, all of the directions, all of the motions of magnetic fields can be oriented in the same direction. That produces constant magnetization. That produces a permanent magnet that has a magnetic field in a sense of direction without having to apply external electrical currents. That's obviously useful. It's useful for compass needles. You can be a Greek navigator in, before the turn of the current millennium or the previous millennium, and still navigate without discovering electrical currents. We use permanent magnets also quite often. Each and every one of your earphones has a little tiny neodymium magnet in it. That, in fact, is the discovery that some of these rare earth elements can produce very large magnetizations, very large magnetic fields in small volumes, has led to miniaturization of the audio equipment and the earphones in particular. If you remember, in the good old days, in the 60s, earphones were this big. You can still buy earphones this big. They seem to be, I guess it must be cool. But well, in the good old days, the technology required use of large ear cups because inside them there was a very large iron-dominated permanent magnet. Neodymium and some of the other rare earth elements can produce the same magnetic fields in a much smaller volume, and therefore you can miniaturize the earphones. The way earphones work is by producing small electrical currents when objects move in a magnetic field. How this exactly works is the subject of another, it's another example of the Faraday law. So one aspect of the Faraday law is the fact that if you apply a current to a magnetized object, you can produce motion. This is again how magnetic locks work. This is the way how electric motors work. Here's an example of electric motor. In fact, it has a rotating part called a rotor, obviously, for rotation, and has two, in this case, permanent magnets with their poles pointing in the opposite directions. So that produces magnetic fields that, in this case, the permanent magnet produces a magnetic field that points in the horizontal direction. If I send the current through the loop of wire wound around this rotor, the current will produce magnetic field inside the wire, inside this spool. And this magnetic field will be pointing along the direction out of the plane of the spool, perpendicular. So as we discovered with the magnetic compass needle, if you have a compass needle and you put it next to a permanent magnet, it will want to orient itself towards, where's my needle? There. It will want to orient itself towards the north pole of the magnet. So by sending currents through the rotor, I can make it a magnet with the magnetic axis pointing out of the plane. And so it will want to orient itself along the direction from north to south, of south to north. So I can use this fact in a fairly clever contraption. These electric motors are pretty clever. The way they work is that you start with some arbitrary orientation, you send the current through, the current will produce magnetic field in the rotor, it will want to orient itself along the north-south direction. But then there's a little circuitry here on the top that switches the polarity of the current as soon as the direction reaches north-south. So if you switch the polarity of the current, now the north-south direction flips from north-south to south to north. And this rotor will want to reorient itself by 180 degrees. As soon as it does that, as long as it aligns it with its new north-south direction, the little switch on the top switches direction of the current again, and the rotor will want to flip and orient itself along the north-south direction yet again. And so you do this for every 180-degree flip, and you can produce a continuous rotating motion. I think I'm told I should turn this supply off, turn this supply on, and demonstrate for you the electrical motor. It needs a little help. We need to start the motion first, I guess, in the opposite direction. You can see bits of sparking on the top. This bit of sparking is, in fact, the little electrical discharges that happen when the switch on the top engages and disengages. That happens sometimes in electrical devices that are energized to large voltage. I can change the direction of rotation by flipping the direction of the current. Rotation happens in the opposite direction. So this is an example of turning electrical currents and magnetic fields into motion, and therefore turning it into a device that can produce mechanical work and therefore produce energy. Mechanical energy. I can turn electrical currents and magnetic fields into physical motion, producing engines and other electrical motors. But then also the opposite is true. As it turns out, if I spin this electrical motor myself, if I apply mechanical work, if I apply external force and spin this rotor, by the fact that this rotor moves in the magnetic field, it will produce electrical currents. Exactly the same electrical currents that I needed to move the rotor with the same speed in the first place. So the process is completely reversible. If I apply external current, I can generate mechanical motion. If I generate mechanical motion myself, this device will produce electrical current. And so that's an example of a generator. A generator is a device that where you produce mechanical motion by, for example, burning coal, evaporating water, and sending pressurized steam at the turbine that's rotating, and this turbine, so this could be the turbine, this turbine is rotating in some magnetic field, generating electrical current. The source of mechanical work is irrelevant. All I need is to produce mechanical force, produce mechanical work, and I can turn that into generation of electricity. Let me demonstrate this for you. Actually, for this, I need a volunteer. We could disassemble this generator, but it's actually much more fun to have a real physical device. So this is an electric generator, hand-cranked electrical generator. And so we can use, instead of nuclear power or thermal power or solar power, another example of renewable technology, which is student power. So if I can get a volunteer to demonstrate their mechanical powers, yeah, come on up. We can use it to generate electricity. So it's a relatively heavy device. It's heavy because it actually has a lot of coils that are now spinning in the permanent magnetic field. So yeah, turn the crank. Oh, actually, let's see, there's an error here, so I guess we're supposed to spin it another way. I don't think it matters. So how is it going? Is it relatively easy? Yeah, and it's relatively easy, but of course it's relatively easy because you're actually not producing any electricity. The little light is not on. I'm not letting you, yeah, so you can go faster. Now if I complete the circuit and actually start producing current, the going gets a little tougher. Oh, put some muscle into it. So now she has to produce a lot more work. Now she's struggling not against electricity, not against friction only, but she's also producing electricity. And that's hard work. And all that work goes into powering a 12-volt light bulb, something like 10 watts or so. Thank you. So this is an example of turning mechanical action, mechanical work, into producing electrical powers. This generator is actually fairly efficient. The efficiency of a human isn't that great, sort of 25% or so. That's our efficiency of turning food, energy we eat, into useful work. So I'm not advocating using humans for generation of electrical power. That's, Matrix and other sci-fi movies. We are not really efficient in doing that. But the electrical conversion of mechanical power into electrical motion itself is actually fairly efficient. If you start with the mechanical motion, then the conversion process can have 80 to 90% efficiency. Electrical motors and electrical generators can be efficient. It's only the question of what the efficiency of turning thermal power, foods, nuclear power, or heat power from burning coal into the mechanical motion. That part in typical power plants is not as efficient. So this again, this Faraday law concept, the fact that you can take mechanical motion to produce electric currents or take electric currents to produce mechanical motion is used in everyday devices. And it all works because of the magnetic fields produced either by moving, currents. The same concept is used in other devices called transformers. This, in fact, is the device that helps us with our electrical power distribution systems. Goes back to the notion of the magnetic transformers, goes back to Nikola Tesla. And the idea is that a alternating magnetic field, or the alternating current in a transformer, can produce a variable magnetic flux in the transformer core that will in turn induce a variable electric current in the secondary winding. One part of the Faraday's law that I didn't specify exactly is the fact that in order to generate electric currents, you need to have a change in the magnetic field. The constant magnetic field is not going to do it. It's the change in the magnetic current that generates additional electrical fields. In effect, this magnetic fields, the devices that can produce electricity, basically have a lot of inertia. They're trying to resist to a change. So, for example, if I turn this magnetic coil on and suck the iron core inside the solenoid and then try to pull it out, the magnet resists me, and resists me quite significantly. It produces force that actually varies with time, and that force is generated by a variable electric current. As soon as I try to change magnetic field going through the solenoid generates additional electrical current that increases the magnetic field, try to resist this change in the magnetic configuration. So in order to generate electrical currents, you need a variable changing magnetic field, and the other way around. If you're producing a variable magnetic field, it can generate a varying electrical currents. And so this is how transformers work. Transformers inherently work only on currents, or with signals, with currents that vary in time. Those are called alternating currents. Effectively, these are currents that vary over time. Traditionally, they vary in a sinusoidal, cosinusoidal fashion, which basically means that the current goes from positive to negative periodically, with some frequency that we know in this country to be 60 hertz, so in other words, 60 flips per second. This frequency is determined by how fast the generator spins. Some generator somewhere is spinning with the frequency of 60 revolutions a second, and that determines the period of the oscillations of the electrical currents to be exactly that. And so the US has settled on the standard so that every electrical generator that produces electrical power is regulated to produce power that oscillates, flips from positive to negative, up and down, at the rate of 60 flips per second. In Europe, the regulation is slightly different. They somehow round the numbers, and so the frequencies are 100 instead of 60 hertz is 50 hertz. It's a nicer round number. 50 times 2 is 100, I guess. That must be the reason. And 60 times 2 is 10 dozen. That's a round number in British system. So the transformers work on a similar principle. If you send the electrical current through the wire and change this electrical current from positive to negative, it will induce a magnetic field in the solenoidal winding. The solenoidal winding and the transformer core will transfer this magnetic field to another winding, where the variation in the magnetic field will induce a voltage on the outside contacts of the winding on the other side. And if you connect this winding to a device, a lamp, a motor, a pressure, a pressure cooker or a rice cooker, then you will complete the circuit and the current will flow in the secondary winding as well. Now, there's an important feature of these transformers, the fact that the magnetic field produced in each of the winding is directly proportional, depends on the number of loops the winding makes in this transformer core. Basically, the more loops you put in, the larger the magnetic field it produces. This is why this particular solenoidal magnet that produces a very large magnetic field has on the order of 100 windings in it. So the more loops I put in, the larger the magnetic field is. On the other side, the effect is opposite. For a given magnetic field, the more loops are produced, the smaller the current I would get on the output. So the ratio of loops in the primary and secondary winding can determine the ratio of the current on the input of the transformer or the output of the transformer, or equivalently, determines the ratio of voltages on the, in the output secondary winding over the primary winding. So if I set up a transformer like this one that has a very large number of windings in the primary, a very large number of loops in the primary winding. There you go. And a small number of loops in the secondary, I can change the ratio of voltages on the input of the transformer to the output of the transformer, and that ratio is exactly given by the ratio of the number of loops. So transformers can step up and step down voltages by a large number. The number is determined purely by geometry of the transformer. If I make my secondary winding to have 10,000 times more loops than the primary, then the voltage on the output of the secondary winding will be 10,000 times larger. So these devices can use to change the amount of, to amplify the voltage, or to change, step up the voltage or step down the voltage. But these devices conserve electrical power. The total amount of electrical power flowing into the transformer and flowing out of the transformer is exactly the same. These devices do not generate power, they transform it. So if you remember what I wrote last time, the electrical power flowing through every circuit, the power, is a product of voltage times current. On this equation above, symbolically I write it that power is V times I. V stands for voltage, I stands for current. So if you create a transformer that increases the voltage by a factor of 1,000, the output current will be reduced by a factor of 1,000, so that the total power flowing in and out of the transformer is the same. Transformers do not generate additional power, they just change the parameters. So this helps regulate the voltages and the currents. If you are trying to increase the voltage by some large fraction, you pay the price of reducing the electrical current that flows through the system. I've showed you this example before, and since it's a fun demonstration, I'll show it again. Again, this is a Tesla coil that has a very large voltage multiplier factor. It draws voltage from the, well, actually, this is the transformer that produces most of the voltage increase. It draws power from the outlet at the voltage of 110 volts. And then this very large transformer steps the voltage up by a factor of, I think, 1,000 or so, producing the voltage on the output of 10 kilovolts or more. Now, if this device then draws an ampere of current, it will produce the milliampere of current on the output. So in other words, the total product of voltage times current is the same. So if I want to get 10 kilovolt, or let's say if I produce a 10 kilovolt output on the output of the transformer, increase the voltage by a factor of 100, current drops by a factor of 100 from 1 ampere to 10 milliamps. Large voltage can produce electrical discharges. So in fact, let me find the button. There we go. The voltage can be large enough to strip electrons from the orbits of oxygen and nitrogen. Those electrons will be again accelerated in the magnetic field, in the electric field. Will strip electrons from the neighboring oxygen nitrogen molecules, producing a large electrical discharge and avalanche-like effect that you can see here. It produces a lightning bolt. Lightning bolts require large voltages, but they don't require large currents. So even though I can produce a large discharge, the current flowing through this discharge is relatively small. In fact, it's small enough that it would be safe for me to discharge through myself, which is something that I can do. The current is enough to light this fluorescent light bulb. The voltage is enough to light this fluorescent light bulb. Fluorescent light bulbs typically operate at slightly larger voltages than incandescent. But the current is too small to kill me, luckily. I mean, it produces a tingle. It was actually kind of slightly uncomfortable. But it doesn't produce significant biological effects. Right? Thankfully, doesn't cause fibrillation. So again, transformers are devices that can increase the currents, reduce, or increase the voltage, reduce the currents, or do it the other way around, increase the current in some circuit by reducing the voltage. And this is actually something that helps with the electrical power grids, something that helps with the electrical power distribution systems. In fact, these days we use alternating currents, AC currents, universally in all devices that are powered out of the outlet are powered by alternating currents. Devices that you use, in the portable devices typically are powered by DC currents. So there's a good reason for this difference. In fact, the first electrical devices, like this one, the first experiments with electricity were typically done with direct constant currents. The reason for this is that it's easy to make a battery that produces constant electrical voltage output. And so the first, again, experiments with electricity were typically done by DC currents. And DC currents are also convenient to use. For example, if you want to power your laptop, you actually want a constant voltage across all of your microelectronic circuits, typically, anywhere from 1 volt to 5 volts, depending on the generation of your semiconductor circuit device. If you power a lamp, you want that lamp to stay on for as long as the switch is flipped. So you want to produce electricity at a constant rate. And so, for things like lamps, motors, and electronics, DC power is actually most convenient. So Thomas Edison has realized that, and in the early 20th century or late 19th century, has been developing techniques for generating large amounts of electrical power, and he was focusing primarily on the direct current or constant current distribution systems. There are several arguments for this. The DC currents, as it turns out, are somewhat safer than AC currents, as I was describing last Tuesday, AC currents, by the virtue of their continuous oscillations, can interfere with the electrical signals that power the human nervous system. Those electrical systems work at the frequencies of sort of 10 to 20 hertz. And so alternating currents that run at the frequencies similar to that, say 50 or 60 hertz, wall output can interfere with our basically nervous system activity and cause damage or cause seizures, or in fact cause fibrillation, stoppage of the heart. The problem with the DC voltages is that it's difficult to change the actual voltage up or down without significant energy losses. And the reason for this is that the most common device that without extra loss of the electrical power can transfer the system, that can transfer the voltage, is a transformer, and that only works for variable alternating currents. So this was realized by Nikola Tesla. Nikola Tesla has designed devices like Tesla coils. He did a lot of research on the transformers. Tesla coil, this one, that generates very large voltages and spectacular sparks. It has a transformer built in it, and it operates on the same principle of increasing the voltage by changing the number of windings in the primary and the secondary loop. And so Tesla also realized that, in fact, generators that work by moving a coil in a constant magnetic field will also produce alternating currents. It will produce currents that also flip up and down. The devices like generators or alternators are very well matched to the power distribution system that operates at alternating currents. And the power distribution system typically have the following features. Usually, if you want to deliver power to your consumer, it's more efficient, economical, from just point of view of infrastructure, is to have a single power station somewhere. The single power station, if it's nuclear power plant, you probably don't want it in your backyard, literally, or you don't want a nuclear power plant in every block, or rather, if you are 20th century industrialist, you're probably using coal for generating electrical power. You probably don't want a little, coal or oil power generator in every yard. It's more economical to have a central large power station that would generate a large amount of electricity and then distribute it through a network of electric wires to the consumers. The problem with this, however, is that any wire that carries electrical current heats up. This was an example. I sent electrical current through this wire and it melted. So any wire that carries an electrical current will produce losses of energy, will produce heat that can either damage wires or just waste electricity, waste electrical power. And that amount of heat is proportional to the square of the current. It's proportional to the square of the current times the resistance of the wire. Is the Joule's law of electrical thermal losses. So if you have a power plant that's producing a lot of electricity, what it actually is producing is a lot of power, and the power is voltage times current, so therefore it produces a large amount of current. And then you want to send it to the consumers and then split this current into several circuits for individual households. So the wires that send the electricity from the power plant to some distribution system in the city will, if they carry large currents, will heat up and therefore lose energy. So the solution to this for the modern power distribution systems is to reduce the current, which you can do if you're operating with the alternating current technology. If you're operating with AC currents, you can use one of the transformers to increase the voltage in the power line, thereby decreasing the current that flows through the wire. This is done by the step-up transformer. You produce voltage at the power plant, typically voltages of sort of kilovolts or so. Then you step up that voltage to voltages that can go up to 100 kilovolts between the two wires. So you run your power distribution system, you run your current through one wire going towards the consumer, and then the return wire going back from the consumer, such a way that the voltage between the two wires can be 100 kilovolts or so. But that means that the current flowing through the wires is smaller than the current produced by a power station, can be smaller by a factor of 100 or more, and therefore the electrical losses from the heat can be reduced by a factor of 100 squared or more, so factors of 10,000. So that makes the distribution systems much more economical. In fact, that fact Edison has realized, that the fact that distribution systems in large cities would lose a lot of power if they operate at DC currents. So he had a solution for this. He had a solution that he would have a power generator in every city block in New York City. And that wasn't even enough. The wires that would carry electricity from this power generation stations were about this big. With several inches in the cross-section copper bus conduits that had small enough resistance, this quantity, to reduce the amount of heat loss. And clearly, this solution is unsustainable on the scales of large countries. One can maybe think about lining the streets of New York City with inch and cross-section copper wires. But if you imagine powering the entire United States, it would require a lot of copper, a lot of material, would be very expensive. So Tesla's solution of using transformers, using alternating currents to produce variable electricity, variable rate of electricity, and using the transformers to change the equation to reduce the current in the power lines and therefore reduce the thermal losses works extremely well. It, of course, has consequences. We now operate all of our power distribution systems at AC. We operate it at 60 hertz and with the power output out of the wall socket of 110 volts, standardized in the United States. Europe uses similar distribution system, except they run at the frequency of 50 hertz and the voltage of 220 volts out of the electrical circuits. So you know that if you go to Europe, you need typically two things. If you want to power your electrical devices, you need a plug that works with European plugs, not the standard American model with kind of two flat prongs, but a model which has kind of two circular electrodes, cylindrical electrodes, spaced out a little bit further apart. There's actually a reason for spacing those plugs further apart. You guys know? So if you look at that's a small aside. Have you ever tried to pull a plug out of the wall in the dark? What happens if it doesn't go? What do you usually do? If you're in the dark, you're trying to feel for the plug. Have any of you got shocked doing that? I have sometimes. It's well. The American plug looks like this, right? So it has two prongs for power, for the actual voltage, and if it's a grounded plug, it has this one big cylindrical plug that's not connected to any power distribution system, but it's connected to the ground. It provides a safe way for electricity to leak out of the device and be dispersed in the ground. But what can often happen is that, this distance is what? Less than half an inch. Human finger can actually fit in, right? Clearly. So, if you're trying to pull this plug out of the wall and, it doesn't go anywhere, there's a tendency to, pull on something you can grab. So there's a tendency to stick your finger sometimes and get it stuck between the two electrodes, leading to electrical shock. In Europe, the electrodes are spaced a little bit farther apart. The finger actually slides through. It's a little bit safer. On the other hand, they operate at higher voltage, which we will discuss. So this concept of trading voltage for power is extremely convenient, but again, it leads us to operate our distribution systems at relatively high frequencies of about 60 hertz. Why 60? You know why we operate at frequency of, well, Europe operates at 50 hertz, we operate at 60 hertz. Why 60? Why not 10? Why not, I know, 157? Any idea? Yeah, exactly. So at a very low frequency, so human brain typically has a reaction time of about 100 milliseconds. So in other words, you can react to pictures changing about 10 times a second. Sometimes a little, you know, some people are faster, some people are slower. You know, hockey, ice hockey goalies have reaction times of faster than 100 milliseconds. They have to catch a 100-mile-an-hour puck. You know, baseball hitters and pitchers have a pretty decent reaction time. But typically, you can sort of see frames changing about 10 times a second, which is why old movies would run at 24 frames a second, high enough frequency for you not to notice the flicker. The high quality video can run at 30 hertz or more. Again, to kind of give you a picture that doesn't appear to be shaking. So the power, if the power was running at 10 hertz, we would be getting light output that would always go up and down. You know, the power produced by electricity goes as voltage times current. So if the voltage drops to 0, sometimes the power produced would drop to 0, and so you would get a oscillation in the amount of light, and you would see flicker at low frequencies. 60 hertz is safe enough, you actually don't see flicker. 50 hertz is sort of close enough. I mean, most people don't see flicker. I don't see flicker in Europe. Some people claim they do. It might be a perception issue. So we pick the frequency so that devices that run at AC current, such as normal incandescent lights, can produce outputs that seems constant to us. So this is designed for primarily for operation with humans. You know, other animals perhaps will have a different perception. So this equation actually is, you know, has other importance. This relationship between the power, voltage, power is the product of voltage and current, is important in other means. If you're designing a circuit breaker, or if you're buying a circuit breakers are designed for specific current. Why are they designed for specific current? Well, it's because typically they're designed, in fact, for specific power. You know, if you're you know, using a device at home, it would generally be rated in power units. You buy the light bulb and it says 100 watts. You buy a microwave and it says a kilowatt. So devices that we care about are typically rated in power units. But we know that we would ultimately plug them into an outlet that feeds 110 volt voltage, and so we can convert the power of, let's say, a kilowatt into the requirement on the current. If the voltage is 100 volts or 110 volts, let's say power of 1,000 watts would be 100 volts times 10 amperes. And so if you want to power a device that draws a kilowatt of power, you need to run it through an outlet that's capable of withstanding 10 amperes of current. And so, you know, sometimes bad things happen if you don't use a device that's not designed for such large current. If you know that the current is this large, you know that the wires have to be thick enough to produce low amount of heat and not melt when you are sending this much current through. So you need to use both a circuit breaker that's rated for this current and the conduits that also rated for the current of at least this much or higher. This leads to certain requirements in electrical safety. You know, if you buy a, let's say, either an extension cord or if you buy a surge protector, if you read, nobody reads the manuals for these things. Nobody reads the little, pamphlets that come with them. But they always say in big letters that you're not allowed, and actually in the US that's a law mandated, it's a government mandated law, is that you're not allowed to plug in an extension cord to another extension cord. You know why? Oh, the reason for this is that if you plug in one extension cord into another extension cord into another extension cord, it makes it very easy to exceed the power rating of a particular extension cord. What often can happen is the following. No, so you take your extension cord, plug it into a wall, it has some sockets in it. And suppose, you plug in, into one extension cord, you plug in, a little light bulb, 100 watts. And you take another socket and extension cord and plug it into your laptop. And laptops draw, 100 watts. 200 watts if it's a relatively old one. And you plug in your, kettle or something. And it's a kilowatt. So now, where does this power come from? Well, it has to come from the outlet. So you can count how many watts each device draws. 100 watts, 200 watts a kilowatt, 1.3 kilowatts has to come in, which means the currents of about 13 amps. So you look at this extension cord and it says a rating of, say, 15 amps. You say, great, this is safe. Now suppose you take another extension cord and it also has a rating of 15 amps, and this has a rating of 15 amps, and you start plugging devices into that. And you plug in another laptop, or your roommate plug in another laptop, and okay, that's 100 watts. And then somebody plugged in a rice cooker that you're not allowed to have in your dorms, and it draws a kilowatt. And it's still fine for this extension cord, or for this trip surge protector. It only has 1,000 watts, 100 watts, 11 amperes here. But this device is also drawing close to 11 or 12 amperes. So now this output will have to be more than 2 kilowatts and more than 20 amps. And some wire on this side will start to cook. So, knowing the rating of your devices, knowing how each device is rated in particular, what the weakest link in the circuit can carry is important. Now, actually, we have a few more minutes. I have a couple of cool demonstrations that I'll get to in the next 5 minutes. But before that, since we're talking about electrical safety, here's a quiz for you. I told you that in Europe uses higher voltages. Europe uses voltages of 220 volts in the electrical outlets compared to 110 in the US. And the question is, well, okay, so I explained to you that the size of the socket, I think, is designed for human fingers, or rather to be larger than human fingers. That's what I think. At least it's designed for safety. The question is, why is it running at higher voltage? What do you think? Is it because it creates less heat in the wiring? Is it because they want to use greater power devices? Is it less dangerous, or is it works better for DC that, as we all know, is used in Europe? So let me start my quiz, and we'll see what you think. I'll give you a minute. All right, so perhaps 10 more seconds. Okay, everybody done? Let's look at the results. Here are the results. Okay, so most of you, okay, 47%, slightly less than 50% thinks A, with a relatively equal amounts in B, C, and D. The right answer, of course, is A. Why is that? Well, the main reason is, again, going back to the, let me kill this first. The right answer goes back to this equation. That devices humans use in Europe and here about the same, you draw about the same power. We can use similar incandescent lights that draw 100 watts out of the outlet. After all, humans in Europe have about the same eyesight as us, so therefore need about the same amount of light, and therefore the same amount of electrical power that produces this light. Shavers, engines, all are rated. Rice cookers are all rated for the same power. But at the higher voltage, these devices will draw lower current. So if these devices draw lower current, that means that the currents flowing into their outlets are also lower by about a factor of 2. Higher voltage by a factor of 2 means currents flowing are smaller by a factor of 2, and therefore the heat dissipated in the wiring system and the electrical distribution system that goes as a square of the current is also reduced. It makes it easier to have thinner wires and therefore use less copper in devices that draw higher voltage and therefore lower current. Of course, it comes with trade-offs. The higher voltage, if you actually terminate it on a human, in other words, if you accidentally stick your finger between the electrical prongs of the electrical outlet, it hurts more. I've done that in Europe and I've done it here. It does hurt more in Europe. So this higher voltage does come with some cost. Now, the last thing that I wanted to show you is another cool example of a Faraday law, the fact that variable magnetic field generates currents. It generates currents in the normal conduits, but it can also generate currents in a regular piece of metal. So this is called eddy currents. This is the principle, the eddy currents. Eddy, that's the river eddies, not the name of some person like Eddie Balfour, the despised goalie for Dallas Stars. The variable magnetic field near the surface of a metal will produce small loops of current in this metal. And any loops of current dissipate heat. So you can use this fact to heat up metallic surfaces. And then if you put something onto metallic surfaces, it will warm up those substances as well. So the eddy current heating, inductive heating, can be used for cooking on the stoves, not microwave heating, but actual inductive heating at relatively low frequency. But it also has other effects. So the interesting thing about the eddy currents is that if you produce these currents by an application of the variable magnetic field, these loops of current will produce magnetic field too. And the direction of magnetic field opposes the direction of magnetic field from the outside. So since the two magnetic, actually not, it points in the same direction rather. So if the two magnetic fields interact, and the interaction will produce a relative force between the conductive material and external source of electricity. Here's an example of this. I have this very large electromagnet here that produces variable magnetic fields oscillating at 50 hertz or so. If I put a magnetic piece of metal, his aluminum dish, on it, it will experience eddy currents, and these eddy currents will produce levitating effects, right? No, levitation, no hands, no strings, nothing on top, nothing on bottom. You can actually levitate frogs this way. I wouldn't advise it. That's not nice to frogs. They tend to move, and that heats them up a little more. The amount of heating, actually, this thing gets warm. The force on the dish can be quite large. In fact, large eddy currents here do heat up this piece of dish. If you touch it, for example, you'll notice that it's a little warmer. So this magnetic interaction can be both used to heat the materials, but also used for levitation, or can be used to propel things. This is the principle of railgun operation. In fact, the fact that you can, if you send a very large electrical impulse through a circuit that includes a piece of metal, the eddy currents induced in this piece of metal will produce large enough force to propel this piece of metal. Here's the demonstration of that. I have my own example replica railgun. Of course, it's safely pointed upwards. We're only shooting in the air. And I have some materials, some little circuits that will experience different amounts of eddy currents. The actual amount of the current depends on the resistivity of this material, so the force that these loops will experience depends on the type of the material. So here's a piece of aluminum. I can send a small pulse of current through the electromagnet. It will induce a eddy current in the loop. And that amount of current is enough to lift my loop. Aluminum is not a very good conductor. It turns out copper is a better conductor. So the force on the current loop is larger. Well, needs a few seconds to charge. But also the amount of the current depends, as it turns out, the resistivity of the material, as it turns out, depends on temperature. So I can change the resistivity of this aluminum block by cooling it down with liquid nitrogen. Resistivity, okay, here's my copper piece, right? It jumps a little higher. I'll cool it too, just for the sake of it. The resistivity changes with temperature. In fact, some materials at very low temperatures become superconducting. That is, they dissipate no heat whatsoever, and they repel all of the magnetic field that is external to them. I'll keep these guys here for a second, maybe a little more liquid nitrogen to induce more cooling. And I'll pour some more liquid nitrogen into this dish that has a superconducting magnet. Well, the dish actually has a normal magnet in it. I have a little superconducting magnet that's also can be chilled. I'll let it cook for a while. At some point, the video camera hopefully switches. This is a little piece of superconductor that also levitates from the fact that the superconductors try to repel all of the magnetic field from their volume, and this repulsion causes large enough force to levitate the superconducting magnet in the external magnetic field. If you come closer, you can watch this little thing. It's, oops, I just knocked it off. It's quite impressive. Now, in the meantime, my aluminum and copper projectiles have cooled off. The resistance now is smaller. The current I can send through them is significantly larger, and that will, hey, come on, somewhat increase the altitude. If I do the same with a piece of copper, give this capacitor some time to charge, I can produce very large forces. And propel this thing even higher. Thank God it didn't hit the little lamp. So to take away messages from this, low temperatures reduces resistance and therefore increases proportional for railguns. And the example of the railgun is here. This can be used for weapons or can be used for peaceful purposes. So I'll see you on Tuesday.